So again, as I have been saying, so here I am talking about G is equal to C is equal to what units, right? And this is our old equation of hydrostatic equilibrium. Now we have discussed this equation large number of times in this class, and this is very familiar. Now already G is equal to C is equal to 1, it becomes even more simple. Fine. Now remember, this is for the Newtonian case, but you have already seen when we were discussing the white dwarf and neutron star that for white dwarf the Schwarzschild metric terms, they don't become that much important. Remember, so GTR effects is not important, but for neutron stars the value is quite significant, but again not more than 1, but significant. So here we are now talking about neutron stars. So since I am talking about neutron star, and I already know that for neutron star the effect of gravity is important, so if I am going to talk about the structure of the neutron star, it is also important that I should talk about relativistic equations of stellar structure, right? Now this is one of the relativistic equations of stellar structure. This is basically the relativistic equation of hydrostatic equilibrium, also known as TOV equation, right? Now look into the difference between the two cases. This is for your normal scenario, non-relativistic Newtonian case, and here this is for the relativistic case. Look into the numerator. The numerator, you will see there is a rho, but here along with rho there is an addition of pressure P. So here there is addition of pressure with rho. Next term M. Here you see along with M there is another term which depends on pressure. So this means now in the relativistic case there are two additions in the numerator, and both additions depend on pressure. So you must try to understand why is it so. What is changing? Actually, the thing that is changing is the fact that in Newtonian case, the source of the gravitational field was mass itself, right? But now, in the general theory of relativity, the source of gravitation is energy momentum tensor, and that energy momentum tensor, it depends on both your density and your pressure, right? So you see here we have got both the addition of pressure in these two terms. What is this? Mass. Mass is basically density. So this thing is quite similar to there. Here we have added a term dependent on pressure. Similarly here we have density. Now here again addition of pressure. So addition of pressure in this case. Next, look into the denominator. There it was just r square, but now the denominator, what is it? Denominator is lower. So what we are seeing overall effect is that the numerator is increasing whereas denominator is decreasing. This means the whole thing becomes larger compared to the Newtonian case. But remember there is a negative sign. So this means that the pressure gradient is now much more negative. Okay? Fine. So this is regarding this fact. Now as I was saying, so we have talked about the numerator, the denominator, the effect, how it changes from when we go to general relativistic case or relativistic case compared to the Newtonian case. And this is the equation of TOV equation. Another very important point, which is that here you see the pressure is there, but where is it in the equation? If the pressure is on this side with plus sign, then this means pressure is still against acting the gravity, right? But now look here, the pressure is on the right hand side, again with this negative sign. So this means now in the relativistic case, the pressure is acting along with gravity. So in a way, pressure is assisting gravity. So if I ask you that a star is collapsing, right? there is no hydrostatic equilibrium, say the star is collapsing. So if it is a non-relativistic star and if it is a relativistic star, in which case the collapse will be faster? The answer is obvious. In the relativistic case, you see the steep gradient and the pressure is acting along with it, so the collapse will be much faster in the relativistic case. Okay, now application of this difference. Look, if I use this Newtonian case, I have shown this to you, and I consider an incompressible matter, nuclear matter, constant density model, right? Then you can show, you will get a value of PR, and this will be proportional to r square minus small r square with some constant term. You can check it for yourself. If, in fact, we have worked on even more complicated density forms, the linear density model, quadratic density model. This is a much more simpler case. Now, what I want to highlight right now is this fact. What is the value of P at r is equal to 0? It is the central pressure. And if you look into the expression you will see that Pc is always finite for all values of mass m. So this means the theory, this Newtonian theory, it does not place any restriction on mass m, right? So there is no restriction. Whereas if I now work out again the constant density problem with this TOV equation, you will be amazed to know what we will get is something like this. PR is equal to some term minus some term, again some term minus some other term. You will get something like this. Now if I reduce to r is equal to 0 case, that means central pressure, you will see that in one of my videos, that is stellar models and integral theorem, I have worked this out explicitly. So in this case, what you will see, again you get some term like this and another term minus 1. Now this is fundamentally different from this form. Why? This form, Newtonian case, was telling me that the central pressure will always be finite. There is no problem with that. But here, look, here I am getting that central pressure had got term like this, subtraction term. Now in physics, whenever we have got some expression with the denominator having subtracted term, this means there is something nice going on, something very drastic. And the drastic thing is that there is a possibility that PC can become negative. But is it realistic? No. So for realistic cases, PC has to be finite. Also, it cannot go to infinity, right? So this places a constraint. And here, so here we have a constraint. And you can see, if you check my video over there, that you will get a relation of m by r less than certain number. So you will get a constraint like this. Again in G by C units, you will get this value is 4 by 9. G is equal to C is equal to 1 units. So you see, there is no constraint on mass m. Whereas the relativistic case, it places a constraint on mass m. And this is very unique. This wasn't over there. And this is purely a manifestation of the general relativistic effects. That's all. Nothing more. বুঝতে পেরেছো?